at how current can give you a magnetic field. Now what's the relationship between the magnetic field, B, and the current running through it? Any guesses? As soon as I switch the current on, what happened there?
Got movement.
They did kick out the way. So it moved that way with the electric field going from there to there. The poles of this magnet are north and south, so the field is going that way. If I was to reverse the direction of the current using the power supply here, what would you expect to see happening?
Go the other way?
It gets kicked out that way. So with the motion of the electrons going that way and the field still going that way, the push is out in that direction. So you've got, how about if we went back to our original current direction with the current coming up, but this time swap the magnetic field direction around. So the field is now going in that direction, the current is still going up the way, how do you reckon it'll go this time? Goes out that way. If we have them both reversed, so if we keep the field going that way, but this time reverse the current direction so the current's going down, where would you expect it to go? Goes the other way. Again, I'm using the left hand. The thumb is still the motion of the electrons. The fingers are still the field. The palm of my hand is the push of the force which is experienced by the charges. Okay, so those electrons going through there experience a force, and that's why the wire moves, either that way or that way. It all happens perpendicular, or in 3 dimensions you would call it orthogonal. You've got motion in 1 dimension, field in a 2nd dimension. The push happens at right angles to both of them in the 3rd dimension. So it's a 3-dimensional arrangement. So the idea is that when that's sitting on there, there's a magnetic field going like that. The motion of the electrons goes like that. And when we switch this on, it moves. So I must have a magnetic field the other way. So the motion of the electrons is across like that, and it's pushed that way. Same sort of thing. You can reverse the direction of the magnetic field, go the other way, or we could reverse the direction of the current, and it would go the other way. Okay, so the same sort of thing applies there. That's the basis of an electric motor, this connection between the magnetic field and the current. So there's an equation that relates these things, and we'll just put it up on the board there so you've got. So if you've got a conductor that's in a magnetic field, quite tricky to draw in 3 dimensions, but I'll have a bash here. So there's the current I running through there. If the magnetic field lines are running through like that, so that's B, magnetic field. If they're arranged at 90 degrees to each other, the force will come out F at 90 degrees to all 3, to the other 2. So current perpendicular to the field, force perpendicular to the current and to the field. The equation that relates that gives you the force is equal to I, L, B, where L is the length of the conductor that you've got in the field there, and you've got the current, you've got the field there. Field is measured in Tesla, or capital T, and it's this equation which gives us the definition for 1 Tesla of magnetic field. Because if you've got 1 amp of current running along 1 meter of length of wire, Guess what the force would be that's exerted by one, if it's in 1 Tesla of magnetic field? 1 Newton, okay? So, running through it. This is fine if everything's orthogonal, if everything's at 90 degrees. The difference happens in the real world when the current isn't at 90 degrees, where there's an angle measured between the two. So if we measured, and you'll be able to do this on Monday when you're setting this up. So if we had the field B running from bottom to top there on the page, and if we put the current through at an angle there, if that was the current I running through at an angle there, what would we have to do to get the component of the current that is at 90 degrees, that is perpendicular? We need to know how much of this current, the current is actually running through like that, how much of the current does cut at 90 degrees across the magnetic field. Yeah, so if we take a triangle, so if you've got I there at that particular length, the effective length that's going there, if that's I, what's that? There, that's the angle that we've got theta in there. So what would be the component of the current which is cutting at 90 degrees? Sine. So it's I sine, so this is going to be L sine theta. So the effective length which is cutting across there is L sine theta. So we actually end up with the full equation for this is ILB sine of theta if there is an angle between them. If the angle between them is 90 degrees, what does the equation become? What's the sine of 90? Just ILB, yes. So it works for any angle, including the angle where that's perpendicular. If theta went to 0, so that the current was running parallel to the magnetic field lines, what would the force be in that case? 0. So if you've got that running parallel, you don't get any force. And that kind of makes sense too. So that's the force that we've got, and that's our definition of 1 Tesla of magnetic field, and that's why I was playing the song Tesla Girls before, which is the one that we kicked.